Hello and welcome back. Today we're going to continue our discussion on trees and tree-based data structures by looking at binary search trees. So I gave a brief introduction last time to what binary search trees are, and I'll pick it up there. Remember that we do have our live Q&A feature over on Piazza, so if you've got questions during the live lecture, go ahead and post to Piazza in the live Q&A forum. Otherwise, if you've got questions afterwards, go ahead and post also Piazza, but in the regular forum. Okay. So today, we're looking at binary search trees, and I do have a visualization over here on the left. We've got basically a binary search tree is, well, first of all, it's a binary tree. So it's a binary tree such that every node, and I'll call it U, holds a key K, such that for every, now this is kind of an inductive property, so it has to hold for every single node. For every node in U's left subtree, or I should just say every node, so not for, but every node in U's left subtree has a key value less than K. Right? And every node in U's right subtree has a key value greater than K. Now you might immediately notice that, well, what happens about ties? What if I've got two nodes in the tree with the same key value? We're not. That's just a technical issue that we're not going to get into. Basically, you can always arbitrarily break ties. So if you've got two objects that are exactly the same, say two portfolios, and you are sorting them by their value, right? Well, if you've got two portfolios with the exact same value, then we'll go ahead and break ties by looking at the last name or something like that. So it's not that big of a deal. You can have binary search trees where duplicate key values are stored, 5 and 5 in a tree, and you just have to be consistent about what you're going to do in that situation. That break ties to the right subtree or break ties to the left subtree. In other words, less than or equal to or greater than or equal to, and stick with it. And you can still use that definition. Okay. Again, the visualization over here is that for every node, now this is not just the top root node. This is for every node. The key K here, every node in the left subtree is strictly less than K. Every node in the right subtree is strictly greater than K. Okay? So that's the general setting here. And in a moment, we're going to see the real power of this. But instead of just drawing everything out here, what I've done is I've grabbed, here we go, main screen. I've grabbed a visualization tool. Again, these are a dime a dozen. There are many and many of these on the web. All you have to do is search for one. And we're going to be using this visualization as well as coding our own binary search tree. But this is what I'm going to start out with here to illustrate why this is so powerful. For example, there are three basic operations for any binary search tree, for any data structure, in fact, right? We want to support all three of those operations. Three basic operations, kind of like CRUD. There's a search, right? That is find a particular node based on its key value. We want to, and that's why we call them binary search trees. If you just have regular binary tree, then searching for something would require pre-order, post-order, and in-order traversal because you actually have to go through the entire tree to find what you're looking for. Okay. But this one, we don't have to go through the entire tree because of the nature of the structure. That everything less is over here, everything is greater over here. So when we actually go to search for something, say in this one, we're going to search for 30, right? We start at the root and we don't have to, and we see 30, we're searching for 30. We see that the root is 37. We do not have to search at all in the right subtree. So we've effectively cut out potentially up to half of our entire tree, just like binary search on an array. But we don't have to have random access here. Okay. Also, we'll want to be able to insert elements, right? Preserving the binary search tree property, or properties if you want, if you call these two properties here. And we also want to delete elements. Now, unlike CRUD, there is no update, although you can certainly think about doing that. If you have an element in your binary search tree that needs to be updated, that could potentially change the key value and change where in that tree it needs to be. So that's why we don't generally call them focus on an update method or an update operation. Instead, what you could achieve the same result by finding the element that you're looking for, removing it, deleting the element, again, while preserving the binary search tree property, and then modifying it and then inserting it back into the tree. So an update operation would actually probably be a series of these two operations right here. These are the three basic operations that we're going to support. Now let's take a look at this tree really quickly here and see that the properties are satisfied. That if I start at the root here, I look at everything in this this left subtree, and it is less. 25, 29, and 30 are all less than 37. Everything over here in the right subtree is greater, 62, 63, 79, 77, 87, etc. But that is an inductive property that holds for everything. If I look at 63, 62 is in the left subtree, and everything in the right subtree is greater than it. And that also holds for 79. 77 is less, 87 is greater. Right? That's an inductive property that has to hold for every single node in the tree. Okay. Now, as you might guess, how do we search the tree? Because, of course, they're binary search trees. Let's go ahead and search for something that we know is in the tree, say 30. Right? Now, I'm going to simulate this in a second here, but let's go ahead and walk through the process using just local information. Like all trees, you start at the root, 37. And the thing that we're searching for is 30, so that's not what we're looking for, right? If the only thing that you could see is, say, this part, right? Then you're not looking at the entire tree. You're only looking at the element 37, okay? You know that that's not the thing that you're looking for, so you traverse to the left subtree. You see, oh, okay, now I'm at 25. So the thing I'm searching for, 30, is greater than 25, so I need to traverse down to the right subtree. 30 is still greater than 29, so I traverse down to the right subtree, and I find the thing that I'm searching for right here, and I stop my search and say, I'm done, here you go. So let's go ahead and simulate that. And the visualization here will show you exactly what I was describing. That it traverses down to the left subtree, then to the right subtree, then to the right subtree, and it stops because it's found what it's looking for. Likewise, let's go ahead and search for 77. We're going to start at the root. We traverse down to the right subtree because it's greater, right subtree, but then we take another shift down to the left subtree to find the thing that we're looking for. Right? Well, we could get lucky, right? We could say, well, what if I were searching for 37? Then I find it at the root and I immediately stop. In other words, I only had to make one comparison to find the thing that I was looking for. To find 30, I had to make one comparison to traverse left, another comparison to traverse right, another comparison to traverse right, and finally a fourth comparison to see that this is the thing that I'm looking for. Same thing with 77. We made 1, 2, 3, 4 comparisons total. What if we were searching for something that didn't exist? What if we were searching for, I don't know, 76? That is clearly not in our tree. So what happens with an unsuccessful search, which can happen? Binary search can result in an unsuccessful search, in which case you would throw an exception or return false or return -1 as the index value that you're searching for, etc. Right? So let's go ahead and simulate this. So we go down to the right subtree, left subtree, but it's not there. So immediately we stop because we've run off the edge of the tree here, and we return false or return null or throw an exception or whatever design decision that you've made that indicates that it was an unsuccessful search. Okay. Now, before we go on to actually implement this, and I'm going to try to implement all three of these today if we can. Let's make some observations. We always start at the root, and we traverse left, traverse right, depending on the relative ordering of things and the thing that we're searching for. Sometimes we get lucky and we can stop short. If I'm searching for 63, right? There's no need to continue your search down to the left or to the right because that's the thing that you're searching for. You're done. So stop. So one thing that we're going to want to do with this implementation is once we've found a successful search, we stop what we're searching for and we return that value or that tree node or whatever we're trying to do. Another thing that we need to keep track of is another stopping condition. The searching for 31, right? When we don't find what we're searching for, when we've fallen off the edge of the tree, we need to stop and return whatever our flag value is for an unsuccessful search. Okay. Let me make sure that we're still on. Yep, we're still on for live Q&A here. So those are our two stopping conditions: either a successful search or an unsuccessful search where we've fallen off the edge of the tree. Another thing to note here is that even in the worst case, that the number of comparisons that we made, once we get to the end of the tree, in other words, once we've traversed the depth of the tree, then we stop, right? Now, it's not this tree is kind of unbalanced in that there are more elements over here in the right subtree than there are in the left subtree. So we're not getting that nice divide in half and divide and conquer every single time. But we are trimming out or pruning roughly half the tree every single time. Now, there are degenerative cases where it won't matter, but we can get kind of the performance of binary search out of this if we have a guarantee that it's going to be somewhat balanced. Okay, random binary search trees or randomly inserted elements are generally balanced just because of randomness, but there's no ultimately at the end of the day, there's no guarantee. And we'll see a degenerative case at the end of the day that you're going to split those things in half each time. But the observation that I want to make is that all three of these operations will be order D, where D is the depth of the binary search tree, or BST for short, right? So, again, some observations here. If the BST is balanced, then D is going to be order log n, because we've already gone through that analysis where n is the number where n is the number of keys, right? And thus giving us order log n performance, right? That's exactly what we were searching for when we started this module. We were looking for a nice data structure that gave us efficient insertion, deletion, and retrieval operations. Unfortunately, in general, there is no guarantee that the depth will be order log n, right? There can be degenerative cases where the depth is going to be order n, right? And we'll take a look at that later today, hopefully by the end here. But I do want to go through these three operations both visually. Now that we've done a visualization of the search, let's do an implementation of the search. Now, before we do that, I'm going to set you up here with my binary search tree implementation. You'll see here that I've extended that binary tree that we were working on yesterday because I want to inherit all that behavior that we worked so hard to put together. I don't want to have to reinvent the wheel, and so this is one of the points of inheritance. A binary search tree will always be a binary tree, so this inheritance kind of makes sense. But a binary tree is not necessarily a binary search tree. Okay. So this the setup of this inheritance makes sense. I don't know necessarily that I would do this in general. I'd probably want to leave because maybe you have very little use for binary tree. I don't know, but in general, I may or may not do this. Now I've already got this set up here where I'm creating the tree that we had before. The tree that was randomly generated by this visualization tool. I spent some time here to set it up so that we have this tree. And in fact, you can check it out. Let's go ahead and print this out. I think that I can print it out. I'm using code that we didn't develop before, but you can see what it looks like here. And you can verify that that 37 is the root, and then the left child is 25, the right child is 63, etc., etc. So yeah, I built it correctly. Okay. And I just built it by setting up the left child, the right child for each one of these things. That'll give us something to actually work with and test out and see if everything works. Okay. But first of all, what we need to do is the binary search tree holds whatever you want. Yesterday we were holding strings. Today we're holding integers. Okay. You can generally hold anything that you want. And how do you tell? So if you are holding anything that you want, say students or student objects or portfolio objects or video game objects or whatever, right? Then how do you tell that these two objects that, oh, okay, well, I'm searching for something and it's less than this object, or it's greater than this object, or it's equal to this object? This is a great use case for a comparator, right? And that's what we're going to make as part of the class's state. I'm going to make it into a private comparator. Private, in fact, I'm going to make it final comparator for elements of type T, because our binary search tree is holding elements of type T. We need a comparator for elements of type T. Okay, and I'll just call it CMP for short. Right? And I'll need to import this. And once I import it, I'm actually going to have to set it because it's final. So I'm going to have to create a constructor here that takes it. So public binary search tree, right? And it will take this comparator, and we'll set this binary search tree's comparator. This .cmp is equal to that CMP. Okay. And now we've got this comparator. That comparator is for whatever type you're trying to store in this tree. So if I create this binary search tree, clearly I'm going to need to pass it a comparator. Again, a lot of this stuff is you might be working on this stuff like right now in your sorted list ADT for your project. So hopefully this is a review. If not, then please use this as a review. So I'm going to give it an anonymous class, a new comparator for integers, right? And this is an anonymous inline declaration where we also provide the implementation at the same time. There's no need to put this into its own class because we're only using it once. It has one use, it has an ad hoc use, and we don't need to make multiple instances of this. So I'm just going to take advantage of the fact that integers are already comparable. o1.compare2, o2, right? And I'm going to return that value. Okay. If this were strings, then you could, of course, use the compare to method as well. If there was something custom like a student object, then this is where you would need to put that business logic. That given student A and student B, how do you put this student before that student? Or if you have portfolio objects, this is where you put that business logic of this portfolio comes before this portfolio because it has a higher value or something like that. Okay. But otherwise, that's our comparator. We're going to keep this as general as possible, not just for integer values. Now, the first thing that I want to do is I want to implement this search algorithm. All right, the one that we already looked at. I'm going to start at the root, and then I'm going to traverse left or right depending on what the comparator says. If the comparator ever returns 0, then that means that I am going to stop, and that's my successful search. All right, and immediately return that tree node or that value stored in that tree node. Okay. Otherwise, if the comparator gives me something negative, I know that I need to go to the left because the thing that I'm searching for is less, and so it'll be in the left subtree if it exists. If my comparator returns something positive, I know that if it exists, then it resides in the right subtree. Right? You can do this recursively, but I'm going to immediately jump to the better solution of doing it iteratively. First of all, we need to define what it is. So actually, I'm going to make this private initially. And we're going to return a tree node, right? And I'm going to search for a particular value, right? T value, I'll call it, right? So when somebody calls search, they're searching for this value. If we find it, we're going to return the tree node that contains it. Otherwise, if we don't find it, then we can return null, right? Maybe we don't want to throw an exception because somebody is asking whether or not this thing even exists, okay? All right, so to set myself up here, of course I'm going to be traversing down. So where do I start? I need to start at the root. The root is a tree node. So what I'll do is I'll create a tree node here, T, and I'll call it the current node, cur for short. This dot root is where I'm going to start, okay? Now, remember my stopping conditions. If I get down to the end of the tree and I've fallen off the tree, then I need to stop, right? That's simply a null pointer check. While current is not equal to null, then continue my search. Either examine the thing that I'm looking at right now or go left or go right, okay? The first thing I need to do is I need to check, is this the thing I'm looking for? Is current the node I'm searching for? Now to do that, all you have to do is ask your comparator, right? If cmp.compare, I'm going to compare the thing that I'm looking for, the value. I'm going to compare that to the current tree node's value. And if that's equal to 0, then they're equal. That means that the value that I'm searching for and the current node's value are equal, at least in the eyes of this comparator here. So I can stop. This was a successful search. I can return the current tree node. Remember, the return type here is going to be an actual tree node. Otherwise, if the comparator is going to return something negative, then I need to traverse left. Right? The thing that I'm searching for is less than the current value, so because it's returning a negative value here, so I'll traverse left subtree to the left subtree. Else, and now to drive home the point that it's going to be greater, I can put this in as a strictly greater, right? So if the value that I'm searching for is greater than the current node's value, then I need to traverse right. Now immediately I did this for demonstration purposes. Immediately what I'm going to do is I'm going to make this a little bit more compact. I don't need to be calling the comparator once, twice, thrice. What I'm going to do is I'm going to save that off into a value, right? Into x. X is good enough, right? If x is 0, then we'll return the current node. Otherwise, if x is less than, otherwise if x is greater than. A good compiler might do this for you anyway, but cleaner. This definitely leads to cleaner code. And I'm going to observe that this doesn't need to be an else if condition, because something is either equal, strictly less than, or greater than, so I don't need to even make that check there. Okay? So I'll traverse left, I'll stop, or I'll traverse left, or I'll traverse right. Traverse to the right subtree. Okay? Looking good so far. Right? Obviously, it's not done yet because I haven't taken care of these things. So I'll traverse to the left subtree. The way that I do that is simply by saying current is equal to current's get left child. Right? I don't have to worry about checking to see whether or not this is null, because that's taken care of by my while loops control structure up here. That once I've fallen off the tree, I come back up here to this while loop, it'll end up being null. And so when it's null, then I jump out of this loop and I'm done. So I don't need to check that it's null here. Otherwise, traversing left is simply just setting current to be current's right child. Right? And that's it. Now, it's still complaining about this because either I stop in a successful search and return the current node, or I traverse left, or I traverse right. What happens with an unsuccessful search? When you fall off the face of the tree, when you fall off the topology of the tree, then that means that your node, current node, will have been null. You will never have found something that's equal, so you will never have returned from it. So we'll return null in this case. And we can document that in our Java docs up here. That searches the binary search tree for the given value, right? Returns null upon an unsuccessful search, right? And so by reading the Java docs, I would know that that's my flag value. It's not going to throw an exception. It's not going to return true or false or whatever. It's going to return the actual tree node that we get out of this search. Now let's make sure that this works. Remember, I've set up my tree down here in this main. What I want to do is I want to search for, what were we searching for before? Let's search for 30. That was the first search that we did. Okay. So what I'll do is I'll set up a tree node for integers. Right? And I'll just call it u. Right? And t dot search, and we'll search for 30. Right? This should result in a successful search. And we can print out u, and we can see that it contains this value 30 here. Hopefully it runs. Yep, there we go. So, looks like it works for that first search. I did make a screenshot of that, so I'll just go ahead and keep it off to the side here rather than going back and forth. The next thing that we searched for was, say, 77, another leaf. Let's see if that works. And it's a successful search. We found that. Let's search for an internal node, say 63. Right? Let's make sure that that one works. That also works. Let's search for another corner case here would be checking that this thing you're searching for, you get really lucky, and you find it at the first place you find it. That's going to be the root of the tree. And that also works. We do want to make sure that this works in all cases. So let's go search for something that we know that's not there. This should end up returning null, and so when we print it out, it will still be safe. It'll just print the word null instead. Right? And that works too. So it looks like we have a pretty good start here on searching a binary search tree. Now, some design notes here. I made this private. I was still able to call it down here because I'm in the same class, but I made this private for a reason. If I've got a data structure, I don't want to have to know the internal workings of that data structure. We talked about this before when we were looking at linked lists and versus array-based lists. We made a design decision there such that we never actually, for a linked list, we never actually return the linked list node itself. That would be called a leaky abstraction. That basically we're breaking encapsulation by opening up the internal workings of our data structure to the outside world. And we don't want that to happen. We don't want you to search for a tree node. Oh, this is a binary search tree. Okay, now I know a little bit about the internal workings. It's not a security issue. It's a design issue. You don't want to have to worry about that stuff. That's the whole point of abstraction, working with encapsulation. You don't want to have to worry about, okay, well, I need to search for a tree node, so I need to know all about tree nodes. Now I need to, once I've got the tree node, now I need to actually pull the value out of the tree node, and now I've got the thing that I'm looking for. We don't want that kind of abstraction. I made this private because it is actually very, very nice to be able to get the tree node if you want to make changes to it, or if you want to reset its parent or its one of its children. But I don't want to expose that to the outside world. So what I'm going to do is I'm going to have a different public search method that's going to return an element of type T. I can name it the same thing. Remember, we've got method overloading. We can have two methods with the same name as long as they take different values, right? And this might not work. We've got a different return type here, but unfortunately, we're searching for this value. We're searching for this value. So I could call this private search or a node search. There we go. Even the different return type here is not going to be a distinguishing factor. It's actually going to have to be something like this. So what I'll do is I'll capture that tree node. I'll just call it u is equal to node search, right, of the value that I was given. And I will need to do a null pointer check here, because if I simply just return u dot get value, right, then clearly an unsuccessful search here, searching for 31. Oops, what's wrong? Search. It should be t's value returned. Oh, you know what? That's because this should be an integer now. Integer. I'll call it. Well, I'll still use u here. Right, there we go. Now that matches. This will result in an unsuccessful search, and consequently, we're going to have a null pointer exception here when I try to unpack it. when I try to get the value out of that node. So I will need to do a null pointer check here. If u is not null, actually I could do this with the ternary operator. If u is null, then I return null. Otherwise, I'll return the value because it's not null. There we go. Nice little compact code there if you've never seen it before. This is an if-else-if condition, basically. This is if u is equal to null, then the value of the expression takes on the first one. Otherwise, it takes on the second one, and then we, in either case, we return. Okay? Now that null pointer exception will end up disappearing. We get null for an unsuccessful search. Those successful searches should still be the same, that we get 30 back from that. There we go. Wonderful. All right. Let's go back and make sure no questions so far. So that's searching. And of course, it's going to be order D, where D is the depth of the binary search tree, because once you've fallen off the edge of the tree, you're done. You can return. Okay. What about inserting elements? Let's go back to our visualization and see if we can insert some of those elements that we were searching for but didn't find. So we didn't find 31, so let's see what that looks like. I'm going to walk along with this. In fact, we can shut off continuously here and insert. Okay. Let me go ahead and step. Oops. Okay, so it goes on without me. I guess I could have paused it. But basically what happens is, well, the first thing you need to do when you're inserting stuff into a binary search tree is, if you're not allowing duplicates, you need to determine whether or not it's already in there. So it's going to be basically a regular search. We'll start at the root. 31 is less than 37, so we go left, we go right, and then we go right again, but find out that before I had inserted 31, it did not exist. So we found where it needs to be if it wasn't already in there. Now, if it's already in there, then we can say, well, throw an exception, or it's a no operation or something like that. Okay? So we will want to re-perform this search, but we'll want to stop short. If I'm searching for 30, then I stop and say, oh, okay, well, it's already in there. But if I'm searching for 31 so that I can insert it, then before it, I don't think I can. Yeah, I can rewind this now. There we go. So there we go. Nice. So let's go ahead and go one. Oops. Rewind it. And right before, there we go. So we're going to stop short here on our search once and see, okay, well, going down one more, then that would be null. And so that's missing. So that's where we need to insert it. We need to insert it as the new right child of 30. Okay. So a little bit different condition than we had before. So I am going to repeat this code a little bit. If we just did a strict node search for this, then I would end up with null every single time, and I wouldn't be able to then change the topology of the graph, because I want the one that was just previous to this. So I'm going to keep track of both a current node and a previous node, and we could actually do this with a node search, but I'm going to go ahead and change it so that I'm not going to, I might want to refactor that eventually. What I can do is I can go with a public void initially, and I'll say insert. And we'll go ahead and take the value that we want to insert. Okay? So the first thing we need to do is we need to find that out if it's already there. Now, I could make a call here to tree node search, and if I get back something that's not null, then I could say, well, it already exists, so no operation return. Right? I could do something like this. If search of value is not equal to null, that means it's already in there, and I'll just return. Right? That's one way that you could handle this. But then that would require, ultimately, if you find out that it didn't exist, and you do need to insert it, then you're going to have to reperform the search anyway. So I'm just going to go ahead and cut the middleman there and take care of it. Right. Oops. There we go. All right. So I'm going to keep track of a current, and I'm also going to keep track of a previous. Now the previous here is going to be null, because if I jump down to the root immediately, then there is no previous, and so I'll update my previous to be the current, previous to be the current, and update my current previous to be the current, and then update my current throughout this process. Okay. All right. So I've got my comparator here. I am traversing down the tree to see what I'm looking for. If I find that it's already there, right? If current is the node that I'm that I'm searching for, and it is value there, then that means that it already exists in the tree, and I don't need to insert it again. So I'll just simply return, and I'm done, right? In fact, we can come back to this and refactor it and give it a little bit more information here, a little bit better design as we go through. Otherwise, I traverse to the left subtree. Now, not only will I need to keep track of the current, but again, I need to keep track of the previous. So previous is going to end up being current. Right? I copy over current so that I now current is now available to move it to its left child, and I'm going to do that under both of these conditions. Okay. When I jump out of this loop, I will have the following situation where the current is now null, but that's where it needs to be. The previous is the previous node that the last one that I searched. So I need to either insert it as its right child or its left child. And so that's just simply going to be another check down here. After I've broken out of this loop, if, and I can cut and paste this. Here we go. If the value is less than the previous's value, right? Remember, the current is now necessarily null. Otherwise, I would not have broken out of this while loop. So I need to compare it to the previous. If the value is less than the previous value, then where do I insert it? Else. And again, I can make this an else if just for illustrative purposes here. If this is less than 0, if this is greater than 0. And by the way, it can't be equal to 0, because if it was ever equal to 0, we would have returned up here. Okay? So what this is saying is that the value is less than the previous. Right, let's look at our example here and see which case this actually is. And then I'll go ahead and fast forward to the end here. 31, that's my value, that's the thing that I need to insert, is greater than 30, so my comparator would end up returning something positive. And so if it returns something positive, I need to put it in as a right child. Right? So insert as a right child. Right? Oops, I'm not well balanced on my parentheses here. Otherwise, if it's less, the value is less than the thing that you're searching for, so you need to put it as a left child. So insert as a left child. Okay. There. Excellent. Now, how do we actually insert as a left child? If you take a look at the tree node, remember, a tree node has a left child, a right child, and a parent. And I've got setters for each one of these. I chose to make it a mutable tree node so that you could actually change it, so that you didn't have to create a new tree node every single time you wanted to change its parent or whatever. So to insert it as a left child, that means that previous's left child is going to have to be what? Well, I don't have a tree node yet. So what I need to do is I need to create one. Tree node T of, I'll just call it U, or the new node. I'll give it a more descriptive name here. New tree node. And holding the value that we want to produce there, or that we wanted to insert there. So my left child of the previous's left child is going to end up being the new node, or its right child is going to end up being the new node. There we go. Now we're not done here. Remember, you also have, the way that I designed this, you also have a parent here. The parent is going to be the previous, right? So remember that over here, we set the right child here, which is fine, and that'll preserve the top-down topology. But if we ever want to traverse back up to the parent, then we also need to make 31's parent. So let's do that. New node dot parent, or get set parent, is going to be previous. And that's the same in either case. So I could do it in both. Why? If you're going to do it in both, you might as well just do it once. All right, there we go. And again, I'm going to refactor this and improve it a little bit. you know that it's not equal, so that you don't have to make another comparator check here. And since you're only making one call, there's no reason to put it into another variable here like we did up here. Okay. That looks pretty good. Before I test it, though, let's think about this return type up here. Hey, that's free real estate. That's a void function. Might we be able to advertise some additional data and make this a little bit more versatile, a little bit more useful? So what I'm going to do is I'm going to change this into a Boolean, right? And I'm going to describe it in the Java docs here. Inserts the given value into the binary search tree, right? If the new value is already new value is successfully inserted, returns true. Otherwise, if the value is already in the BST, it is not inserted, and it returns, and we return false. All right. Technical writing skills, go ahead and change that so that it's a little bit better. So obviously with a successful search, that's an unsuccessful insert, so we end up returning false. Down here, if we do insert it, then I'll end up returning true. There we go. So now let's test this out. Same as before, there's my searching. Let's go ahead and go with insert. Remember that 31 is not in there. So we'll see if that's an insert. And I'll go ahead and capture that. Boolean b is equal to this. And I'll go ahead and print out to see if this works. Println b, and then we'll also print out, well, there's nothing really to print out here. We'll print out that it's either true or it should be true because it was a successful insert. Now let's go ahead and search for it. If it actually ended up in there and we didn't make any mistakes, then we should be able to search for it now that it's already in there and print it out again. So my expectations here are 30 from the previous search. True, because inserting 31 will end up successful as the right child of 30. And 31 will end up being a successful search after that, printing out 31. So 30, true, 31 should be our expectation. Excellent. And if we print it out, we can actually look at the topology of that to see if it matches what we got over here. 31 being the new right child of 30. Let's run this again and see what it prints out as the topology. So there's the second time that we've printed it out. 31 is now a child of 30. So it looks like it works. Of course, don't rest on your laurels here. You want to make sure that you are, what happens with an unsuccessful insert. Right? There we go. So here I would expect 30 false because it actually didn't insert it, and then 30 again because it's still going to be a successful search. So 30, false, 30. Good. What about something else? What about, what else did we do? Say 76, just to make sure. There we go. We insert it, and it should end up being a successful search. So 30, true, successful, and then a successful search. Successful insert, successful search. I'm convinced that this works. Okay? Of course, you'd want to definitely do a much better testing, a whole testing framework like JUnit or something like that. So the insert preserves the binary search tree property, right? The way that we implemented it. Now, even that, if you want to prove that mathematically, you come up with an inductive proof showing that you have in fact it's not that difficult, but it's beyond the scope of this course. You need to show that the binary search tree property is preserved. Okay. The last one is a little bit more is the most difficult, but before we do that, remember that I claimed that all three of these operations are going to be order D, where D is the depth of the tree, and hopefully you can see that here, because if you're going to insert something, you always insert as a leaf, right? So in general, you always insert a new element as a leaf, right? Existing elements. All right, inserting the same element, inserting duplicates basically, can be treated as a no operation. Right? And in either case, since you're always going to be inserting as a leaf, then at worst, right, you could get lucky and say, oh, well, I want to insert 37. Let's see what this simulation does. 37, here, let's insert 37. Inserting it finds that it's already there, so, oh, okay, it's going to allow duplicates here. Okay, I was not expecting that, but of course it's always going to, hopefully it's being consistent about it, and it's always breaking ties to the right. Let's find out. What about if we wanted to insert 63 here? Then if I'm right, then it would be end up going right, right, okay, well, then right, then left because 63 is less, then left because 63 is less. So let's see what this does. 63, right, breaking ties to the right, and there we go. Okay. So this visualization is allowing duplicates. My implementation so far is not allowing duplicates by checking that. In either case, and no matter what design decisions you make for how your data structure will work for the specifics, all of these operations are going to be order D because you are always inserting it as a leaf. So in the worst case, you end up going all the way down to the bottom of the tree, inserting as a leaf into the deepest part of the tree, like in both of these cases here. Sometimes you'll get lucky and insert, say, even with a successful insert, if I inserted 21 up here, I didn't go the full, it's not going to go the full depth of the tree here. It's going to go something shallow, but remember, we're interested in the worst case scenario here. In the worst case, it's going to go the entire depth of the tree. So it's going to end up being order D. And as we've already seen from a previous analysis, if it's more or less balanced, then it's going to be an order log n performance. Okay? Finally, deleting elements, and this is the last thing that we'll do today. So let's go ahead and delete 63 here. I believe that this does support deleting. Oh, okay. I've got to select a node here in this visualizer, and then I've actually got to delete it. All right, so it actually hid some of the details there. The first step is going to be that you need to find it. Right? If you're trying to delete something that doesn't exist, for example, I want to delete 23, right? 23 does not exist in this. So it would necessarily mean that I need to search for it and find, oh, okay, well, it doesn't exist. So I can't delete it, no operation. Or you could throw an exception. You asked me to delete something that doesn't exist. You should have checked before that, so I'll throw an exception. Or I'm not going to throw an exception. I just want to say, oh, there's a no operation, and we can return a Boolean. It had no effect. Or true, it did have an effect. But so the first step is going to be that you need to find the thing that you're looking for. Luckily, we've already implemented that functionality. Once you've found it, like when we deleted 63 over here, there was no problem if it was a leaf. So if it's a leaf, then just delete it, right? So step one, find the element. And again, if it doesn't exist, then you're done. You can simply just return. Step two, delete it. Right? There are a couple of cases here. So, well, here, I'll go ahead and preserve that. Step two, delete, based on cases. Case one, if it is a leaf, simply rearrange the the references. Okay? So let's implement that. We're gonna go over this, and we're going to do this piecemeal. We'll take care of the other cases here momentarily. But let's just go ahead and, for convenience, I'll just go up to the top here. So public, I'll return a Boolean, and that'll just be advertising the fact that you did change the tree, you successfully deleted it, or you didn't change the tree, you tried to delete something that didn't exist. So delete and t value. That's the thing that we're trying to delete. So step one, make sure that it exists. If it doesn't exist, you're done. Right? So this dot node search, right, for that value, I'm going to capture that. I'll just call it u. Right? Now, if u is null, right, then you tried to delete a non-existent node. So I'll just simply return false. Right? And I can put that up here into Java docs as well. That attempts to remove the node in the BST with the given value. If removal is successful, if removal results in a change of the tree, true is returned. If no effect, false. Right? There. Okay? So I immediately return, I don't need to do anything else. Right? Otherwise, we do need to delete it. So if u is a leaf, so if u.leftChild, or if it doesn't have a left child, and u does not have a right child, right, then I can just simply delete it. Delete it by modifying the parent's reference. Right? So what is my parent? Well, I'm glad that I kept track of that, because I don't have to do another search for the parent of this thing. I can just go back up to the parent, because I designed my tree node here to have a left child, a right child, and a parent. Okay? All right. So if it's a leaf, it doesn't have a left child, it doesn't have a right child, then I simply need to set the parent, u.getParent, set left child to null if I'm a left child, right? Otherwise, if I'm that is you, and I'm getting not the pronoun you, but the letter u. So now I'm also regretting calling this u. Let me go ahead and call, well, it's a node, so we don't like to call it n, because n is usually used for a quantified value, right? Right? There are n elements in a set. U, w. That's just two u's. So a tree node t, right there. It's a tree node, so we'll call it t. Okay. So if it's a leaf, delete it by modifying the parent's reference. I'm t is I'm a left child. So if t is equal to u t's parent's left child, then I'm a left child, so I set my parent t.getParent set their left child to null, effectively deleting me. Now, of course, you could also say t.setParent to null to sever the connection the other way. That's not necessary. In some programming languages, that's necessary, but in Java, it's not necessary. That once that reference to the object t is gone, then it's available for garbage collection, and you don't have to worry about it. Okay. Although there is a potential for memory leaks there later on, if you end up deleting this node, the parent node, then yeah, you'd end up having something with a reference to it. But well, no, transitively, there's no reference to this one, so therefore there's no reference to this one. You don't need to worry about it. You let the garbage collector take care of it for you. Else if, what if I'm a right child? Then I need to set my parent's right child to null. Else if, well, we already know that it's a leaf, so we don't need an else if condition here. I'm either a left child or a right child. There's no other situation. So t.getParent set right child to null. Right there. Okay. Now we do have two other cases here. Else if. What if I'm not a leaf? What if I'm an internal node and I have a left child? What if I'm an internal node and have a right child? Right. So we'll take care of that later. I just want to make sure that I'm getting this. And since we're pressed for time, I don't know if I'm going to complete this today. But ultimately here we'll go ahead and return true, just so that this compiles. And let's go down here and see if it works for that one particular case. Remember, 76. When we insert it, would end up getting inserted as a left child over here. So that's a case where we end up removing just something that's a leaf. Right? So let's go ahead and t.delete 76. And then we can check for it again, see if it's a successful search. In fact, we can also capture that Boolean value. And system.out.println. We'll go ahead and print that out. I do need to insert it, so we'll just end up paying attention to the last things that it prints. I inserted it up here, and there is a successful search. So deleting it should also be a successful search, meaning that B is going to be true. And if I search for it after I've deleted it, then that means that this should end up being an unsuccessful search, outputting null. So let's see if that works. Right. True and null as I expected. Right. Now this is not going to work if it's not a leaf because I haven't done that situation yet. Okay, but we could also go back and check to see other things. 62. We never we could check. 62 is certainly going to be a leaf node. And true, and then null. Good, it still works. Okay. Now, what about another case? What if we wanted to delete, say, 30 here? Okay, let's go ahead and try deleting that node right there. Right? That's not a leaf node. So we'll go ahead and try to delete it. All we do is promote, it's not a leaf node, and it only has one child. That's the other condition that I need. If it has one child, then I can just take that child and promote it up like we did right here. 62, similar. If I'm going to delete that, then I can just promote 37 to be 63's new left child. Okay? So if it only has one child, then you can do this pretty easy. In fact, if it only has one child, then what does it look like? If I just looked at 25, 29, and 31, what do I have here? I have a mini linked list. And how did we delete something from a linked list? We simply just made its previous point to next, and its next point to previous. Right? And when we delete that, you see how it works. So let's go ahead and take care of that situation. All the way back up here at delete. So it's not a leaf. In fact, I would go back and refactor this, a tree node, so that you would encapsulate this logic over in here in this tree node to say that it is leaf, right? In fact, let's do that because it'll look way nicer. Right? All right, so has parent, has left child, right? We can also insert here public Boolean is leaf, right? And I'll return. Do I have this dot has? If I have no left child and I have no right child, then I am a leaf, right? And it's true. Go back over here, change this. If it is a leaf, if U, or T is what I'm calling it now, is leaf. There we go. Make sure that it's still the same, true and null. I didn't break anything. Regression testing there, right there, though it is ad hoc. Else, I'm going to need some conditions here. My conditions here are going to be that I'm not a leaf, but I only have one child. Let's take care of the situation where I have a left child but no right child. Else if T dot has a left child and T dot has right child but negated, so I have no right child. Okay, or T only has a left child. Promote it. Right? And the way that I'm going to do that is if I'm promoting this up, that simply means that my parents. Well, here let's see. I have a left child means that 63 here. I have a left child. Oops, I don't have an example over here. But let's see. Let's insert 36. Fast forward. Oops, no. Darn it. 20, let's go with 20. There we go. There. So 21, I want to delete 21. It has a left child but no right child. So I need to get its parent, and it is a left child, so I would end up setting that equal to 20. 20, I would end up setting its parent to my parent, right, before I'm deleted. Okay, so set t's parent to t's left child. No, set t's parent's child, that is going to be a left child or a right child, to t's left child. Right, and you can kind of see that you're getting lost for the trees here. So it might be helpful to just set up some tree nodes here. No pun intended before, by the way. Parent is equal to t dot get parent. So I don't have that, but these bunch of gets, right? The left child, t left child. I'll just call it left dot get left child. Right, there we go. And so what I need to do is I need to say that the parent dot left or right child is equal to the left. But let's take care of the easy thing first here, though. Left dot set parent to t's parent, which I've already stored into another variable here. Now there are going to be two situations here. Remember that I think I said it yesterday or said it last time. There's an old brain teaser. A guy walks up to a portrait and he says, "Amazing, I know this person." And somebody else says, "What? How do you know them?" Well, brothers and sisters I have none, but this man's father is my father's son. So who was in the painting? It was the guy that was talking, right? It's a self-referential kind of thing. So you have to be very careful here that parents and left child and right child, when you're looking at your parent, you don't know if you're the left child or the right child. We need the logic to determine that. So is T the left child, and so that that the left child then becomes the new child of the parent of T's parent, so it's grandparent, right? So you need to determine which one of those cases it is. So if T is the left child of the parent, right? So if T is equal to parent dot get left child, right? And we can do an equals here because that they should be the same thing in memory, right? We don't have to waste time using the equals method, which is overridden successfully, and I did it already. Else, so if T is the left child of the parent, that means we need to set the parent's left child to left, right? So that's why I mentioned that poem there, that brain teaser poem. You start to lose all these references all around. So set the parent's left child, parent dot set left child to left. Otherwise, T was the right child of its parent, so I need to set T to the left child, to the original left child. So parent dot set right child to the left. All right, there we go. And likewise, it's just going to be a mirror image of this if T only has a right child. So let me go ahead and grab all of this stuff. And we just need to reverse everything. So if it doesn't have a left child and it does have a right child, then T only has a right child, so promote it. Set T's parent's child, left or right, to T's right child. Right? So parent, now right, and I get the right child. Right, set the parent to that parent. If T is the left child of the parent, then set the parent's left child to right. Otherwise, set the right child to right. Right? There we go. All right. Now this is the tree over here, and I've inserted 76. We can go ahead and get rid of that. Let's go ahead and delete something that is internal. So 29 here. Right. If it was successful, then we will have deleted it, and the topology should look something like 37, 25, and then immediately goes down to 30. So to verify that topology, I'm going to print out the entire tree, and we can see that 29 hopefully will be deleted. Let's go ahead and do that now. All right, there we go. So true, and then when we tried to search for it after deleting it, we get null. Now, let's see if the topology is correct. 37, and then the left child is 25, and then the right child of that is 30. Excellent. It still works. Right? That worked for us. Now, we will want to take care of the other, testing the other situation where we're deleting something that has a left child. So to do that, I'm going to end up inserting 76. Let me go ahead and roll this back. Let's see, t.insert 76. And that'll end up having a left child over here on 76. So when we delete 77, then it should be 79. Then when we deleted 77, after we've inserted 76 on the other side, then we'll get a topology with 76 as the left child of 79. Let's see if we do. Right there. 76 is the left child of 79, right? And 87 is still the right child. So I'm convinced this works for at least 3 out of the 4 cases, with one of those cases being the same. So let's review that. Case 1, if it's a leaf, simply rearrange the references. Case 2, if it has only one child, simply promote that child up. Right? Case 3, if it has both children, then what? Right? So I'm not going to be able to implement this today, but let's go ahead and see how this visualizer does it. Let's go ahead and delete the root here. Now that's going to leave a hole in this tree. Before I visualize this, let's think about what we can do here. Can I promote 25 up? That's the knee-jerk reaction of most beginners. But what if I do that? It's still going to have a left child. It's still going to have a right child, 21 and 31 over here. And then it'll end up having another child over here where we end up pruning out this entire tree. We don't want that to happen. We don't want to lose half of our tree by simply deleting one root or one node. And you can't violate the binary search tree property. You can't have 3 children. You can't have 21, 31, and 63. So what could we do here? Right? I don't want to. I want to have what's sometimes referred to as a minimal change property. I don't want to disrupt the topology of this tree too much. I don't want to have to cut down the tree and then try to reassemble it or something like that. I want the minimum amount of change. So let's see what this visualizer does. Let's go ahead and delete 37. What's it doing there? It's going to the right subtree and then finds 37 and promotes that up. Right? Okay. That was kind of cool. Let's go ahead and do that again. What if we were to delete 37 again? It has both children. So it's going to the right subtree and it's finding 63 and then promoting that up and then ending up deleting it and promoting that up. So can you see the pattern here? What about, let's delete 63 again. Let's go ahead and delete the node once more. It's going right, then it's taking 77 and promoting it back up, deleting that as a leaf. If you notice the pattern there, every single time what it did is it went to the right subtree, and then it found the minimum element in that right subtree. And then it promoted it back up to the top here. Okay? So to end the day, let's go ahead and go back over to the overhead here. And let's understand what that's actually doing. Right? So if you want to delete a key, K, but it has both children. It has a left child and it has a right child. And those children might have entire trees hanging off of them. Okay? What it ends up doing is it ends up going to the right subtree, and then it goes all the way to the left to find the minimum element. Now, that's not the minimum element in the entire tree. That's the minimum element in the right subtree. Why the minimum? Well, you know that that's going to be less than everything else over in this tree. So if you put the minimum up here as a replacement for the thing that you're trying to delete, then you preserve the binary search tree property. This minimum was greater than everything hanging off this left subtree. Otherwise, it wouldn't have been in the right subtree. So by putting it up here, it's still greater than everything over here. But by selecting the minimum in the right subtree, that means that it is less than everything over here in the right subtree. Excellent. Or alternatively, you could mirror this and go to the left subtree, then all the way to the right to find the maximum, which is going to be greater than everything in the left subtree and less than everything else in this right subtree, and so you can promote the maximum. Right? Again, if you look at this as, in general as a topology, there's a tree hanging off of this left child, there's a tree hanging off of this. You simply go to the left and go all the way to the right till you can go no further. Or you go to the right and go all the way to the left until you can go no further. Right? Now you might be asking yourself, okay, what happens if that minimum, here's my minimum in the left subtree. I'll go ahead and focus in on this. Here's my minimum, right? And we came from some parent that was a left child. What happens if that has two children? You can't simply just take this and promote it up to the top. What happens if there's a left child and a right child? We're back to square one, right? This can't happen. If the minimum has a left child, then that means that by the binary search tree property, L is less than the minimum. So necessarily, this thing cannot exist. You could have a situation where the minimum has a right child. You could have a situation where the minimum has no children at all. Right? But guess what? We know how to deal with those. Those are the first two cases. If it's a leaf, then simply just delete this, hold this into another variable, right? A temporary variable, where then you promote that back up. You exchange that with the thing that you're trying to delete. Or if it only has one child, well, then you can promote it up so that it ends up looking like, if this is the parent, then R ends up, and there might be things hanging off of R. R then becomes, it replaces the minimum. Right? Likewise, if it's the maximum in the left subtree, necessarily there cannot be a right child. So it either has no children or one child, and we know how to deal with those. Okay. Since we're at the end of our hour and 10 minutes here, I will not implement those. Instead, I'm going to leave those it's a little bit more complicated, but I'm going to leave that as an exercise for you. Okay? All right. When we come back next week, we'll look at the last data structure, which are heaps. Again, the binary search, we'll motivate that with an example that I intended to do at the end of the day here, where you have a degenerative binary search tree, where you just end up inserting everything all the way to the right or all the way to the left, or the depth is order n, right? It doesn't necessarily have to be all the way to the right, all the way to the left, but you end up with a linked list, right? You're back at square one if you have an unbalanced binary search tree, in which case the depth is now linear, and so you're back at square one with a linear search on a binary on a linked list. Okay. We'll discuss how we can partially address that next time. Have a good weekend.